Delaware Tech, Chemistry 100, Chemistry 110, Osmosis, Diffusion, and Dialysis. Before we talk about osmosis and osmotic pressure, let's talk about a concept called colligative property. A colligative property is a property of a solution that only depends on how many particles are dissolved. In other words, what concentration of the solute you have. And it is not dependent on what those particles are. In other words, 1 molar of compound A in solution will behave the same way as 1 molar of compound B in solution for the colligative property in question. And before we talk about osmosis, we have to talk about what's called semi-permeable membrane. A semi-permeable membrane is a membrane. You can think of it as a sheet of plastic in some cases, but there are many other versions of semi-permeable membranes. But it's something that has microscopic holes in it, holes that are the size of molecules, that will only allow certain small molecules to pass through, but not other molecules to pass through. So it's permeable to those molecules, but not to all molecules, hence the term semi-permeable. And your cell membranes, the membranes that surround every one of the 30 trillion cells in your body, are all semi-permeable membranes. They let certain substances pass through, like carbon dioxide gas, oxygen gas, and water, but they don't let other things pass through unless they're being helped. Larger molecules or charged ions do not go through the membrane without some kind of assistance. So membrane diffusion is the passing across that membrane of any substance. So if a substance is going from one side of the membrane to the other, we call that membrane diffusion. Sometimes we'll say diffusion for short. It's similar to gas diffusion, but it's through a membrane. When that diffusion is the solvent molecule, we call that diffusion osmosis. So usually we're talking about water being our solvent. So when water is the molecule going through the membrane, that is known as osmosis. So osmosis is a special kind of diffusion of just the solvent molecule. And for your purposes, the vast majority of the time we'll be talking only about water as a solvent when we're talking about osmosis. And the way the water travels is not just in one direction. It can go back and forth, but it will favor going from the dilute side to the more concentrated side. So if you have a lot of salt or sugar or whatever molecules are on one side of the membrane and you only have a little bit or none on the other, the side with none, the water on that side will flow through the membrane in an attempt to dilute out the solution on the concentrated side. The goal being that it is much more energetically favorable if both sides have the same concentration. And the water will move across that membrane in an attempt to dilute out the concentrated side to make both sides about the same. So osmotic pressure is a colligative property, so it doesn't matter what the substance is that's dissolved, it just matters how much. And it is defined as the pressure required to stop the solvent, in this case water, from passing through this semi-permeable membrane. So remember, if you have a lot of salt or sugar or whatever is dissolved on one side, there's a lot of pressure that the water on the dilute side will have pushing it into the more concentrated side to dilute it out. And the amount of pressure it takes to stop that from happening is the osmotic pressure. And you may have heard this term when people are talking about something called reverse osmosis, which I'll talk about in a minute, which is where you're forcing water to go in the opposite direction that it normally would. That's why it's called reverse osmosis, in order to make pure water. So osmosis is the water going to try to dilute out the concentrated side, and you end up with more dilute on the concentrated side as a result. So here's an example, here's a little model of osmosis. You can think of the red particles as the small water particles that can go through these microscopic pores in our semi-permeable membrane. But larger molecules shown in yellow and green can't go through that membrane at all because they're just too large, or maybe they're charged and they can't make it through the membrane. But the water can go back and forth to try to dilute out the right side of this system. So remember, osmotic pressure is the pressure required to stop osmosis. And we have a formula for this. Pressure from osmosis is P, but it's the Greek letter P, the capital pi. And it's equal to I times M times R times T. Now, what are all these values? Well, the pi is the osmotic pressure, just the Greek letter for P. The M is our concentration in molar, so that's the number of moles per liter, or the N per volume. And I is something you haven't heard before called the Van't Hoff factor. And the Van't Hoff factor tells you how many particles each solute molecule or formula unit will turn into when it goes into the water. And I'll explain that in a second. T is the temperature, and temperature is always in Kelvin. And R is a constant, a universal fundamental constant called the gas constant. And I'll give you the values for that. So molarity is moles per liter, or N per V. That's another way to think of molarity. So our gas equation, if you remember from gas laws, this was from the ideal gas laws, which we don't really cover much in Chem 100. It is covered extensively in Chem 110. But remember the equation PV equals nRT. Well, if we solve for P, we get P equals N, the number of moles, times R, the gas constant, times T, the temperature in Kelvin, divided by V, our volume in liters. But you'll notice there's a part of this equation where N is divided by V. Well, that's just our concentration, our molar concentration. And we have to correct the molar concentration for this I term, because if you have a molecule or a formula unit that's dropped into water and it splits into two, you're going to end up with two particles and twice the concentration that you think you added. Or if it broke up into three particles, 3 times the concentration you thought you added. So we correct the concentration for the I value. So I times N is our what we call our effective concentration. The concentration of the actual particles, not the whole molecule or formula unit that we threw into the water. And so this is where we get this equation from. It's just a modified version of the ideal gas law. In Chem 100, we're not going to worry about using this equation, but for Chem 110, you definitely should know what it is. But the important part here is this. You'll notice that molar concentration is part of the equation for osmotic pressure. And that means if the concentration goes up, the amount of salt or sugar or whatever you have in the water goes up, that will result in a higher osmotic pressure. It will be harder to stop water from coming in and diluting that material the more concentrated you have that solution. So here's an example of another semi-permeable membrane shown in red. And we have two solutions here. We have the solution in blue on the right, and this is a solution that has very little or no solute dissolved. So you can think of it as pure water. And on the left is the yellow solution. This is a solution that has a high concentration of solute. So what you would expect is that the blue water on the right will come rushing through the membrane to try to dilute out the solution on the left. So I'll start the video again. At first they start off at the same level, and as time goes on, the solution on the right, the water on the right is passing through the semi-permeable membrane to dilute out the solution on the left. And this will continue to go until there's a balance between how much pressure from the water going through the membrane due to osmotic pressure, and when it balances out the pressure of the weight of so much water on the left forcing down on that container. And when those two balance out, it stops. Now, you don't have to know the details of this, just know that osmotic pressure increases with increasing concentration of solution, and that it is defined as the pressure that is required to stop this from happening. Now, this is actually very important when we're looking at cells taken out of the body, or even in some cases cells in the body if we're adding excess solvent. So we can have several different conditions for the cells. We can have a condition where we take cells, say red blood cells for instance, and we put them in a container, and we can have a concentration of solution that we add to the cells that's the same on either side of the cell membrane. We have a certain concentration of salts and sugars and whatever other molecules are inside the cell. And if we put that in a container that has the same concentration of those solutes in the beaker, that is called an isotonic solution. Iso meaning equal or the same. Tonic, in this case, will mean the concentrations. So an isotonic solution is a solution that cells are very happy to be in because the concentration of everything on both sides, on the inside and the outside of the cells, are the same. So there won't be any net flow in the cell or net flow out of the cell, so the cells are happy. But you can also take cells and put them in a situation where the outside of the cell, and this is the diagram on the right, the outside of the cell has higher concentrations of sugar or salt or whatever, and as a result, the solution is hypertonic or higher concentration, and the cell relative to that solution is hypotonic or lower in concentration. Hypo meaning less than or lower than, hyper meaning greater than or more. We can also take cells and put them in, say, pure water or water with not enough salt or sugar in it. And that is called a hypotonic solution, a low concentration solution relative to the concentration in the cells. So the cell in this case would be hypertonic relative to the solution. So you can have all three of these situations under different conditions. And what you don't want to do is you don't want to add pure water to a person's body through an intravenous line. You don't want to give them a bottle of intravenous fluids that's just water, because you'll end up putting hypotonic water surrounding the red blood cells in their veins, and that will cause damage to the red blood cells. At the same time, you don't want to put too much salt in your saline solution that you're giving to your patient. Otherwise, that will cause problems, and I'll show you those on the next slide. So really, you want to give what's called an isotonic solution, and that's what our normal buffered saline is, or our glucose saline is. They have roughly the same concentration of salts in that saline solution as are found in normal human blood. So in the case of the hypertonic solution, it's saltier on the outside, so the fluid from the inside of the cells will flow out. So the cells will actually collapse because the liquid is going outside, the water is moving to the outside of the cell. Whereas in the hypotonic solution, there'll be a net movement into the cell, and that will cause the cells to rupture and explode. And in the case of red blood cells, that's called hemolysis. Hemo meaning red blood cells or blood, and lysis meaning breaking apart. So here's what this looks like. So if we put it in a hypertonic solution on the left here, that means there's a lot of salt in this solution on the left. We end up having water leaving the red blood cell, and the red blood cell kind of collapses on itself. That's called crenation. Whereas on the right side of this video here, we have water flowing in because the water on the outside of the cells is hypotonic. It might even be pure water. And as a result, it's flowing into the cell and will keep flowing in until the cells will rip apart. And you definitely do not want this in a human being or in any animal you're giving fluids to. Otherwise, the cells will rupture, you get hemolysis, and all these broken red blood cells will suddenly clog up the veins, and this will cause a lot of damage to the body, including organ failure. So, osmotic pressure, remember, it's moving of the fluids across the membrane, this diffusion of your solvent across the membrane, and people can take advantage of this using a process called dialysis. So this is a process where we have a semi-permeable membrane, and it might be shaped in different ways, and we want solvent, or water usually, and maybe some small molecules to pass through the membrane, but we want to keep the big molecules on the inside. So it's very similar to osmosis, but it also includes other small molecules. So it's a more general diffusion of the particles, and a lot of ions can pass through too sometimes, as long as they're completely hydrated. They're surrounded by waters, and the holes are large enough for that to happen, but that won't always happen. And so you have a mixture here of osmosis, which is the diffusion of the water through the membrane, just general diffusion, which is anything through the membrane, including small molecules that are small enough to go through the holes, and then a process called ultrafiltration, which is this difference because small molecules can go through, but large molecules can't. So you can think of the membrane as a filter on a very microscopic scale. So it lets tiny molecules go through, but it filters out larger molecules from passing through the membrane. So dialysis includes all three of these processes. So in a laboratory, in say a biochemistry lab, you might want to stir in large amounts of pure buffer solvent past a membrane bag, what we call a dialysis bag, that's made of this semi-permeable membrane, and then you can flush out the smaller contaminants like the water and the ions and other salts, as well as small molecules that you don't want, leaving only the big components that you do want. So what does that look like? Well, we make a bag of this semi-permeable membrane. We tie it off at the ends with string typically, and you throw this bag in a big beaker of your solvent, the solvent that you want your large molecules inside the bag to be dissolved in, not all that salt and small molecules that are mixed with it currently. And what you do is you stir this solution, and it takes about 4 to 8, maybe 12 hours for it to go to completion. And eventually, the solvent will flood into the center of the bag, trying to dilute it out. But at the same time, the small molecules on the inside of the bag will come out of the bag and start washing into the beaker. And after a while, those small molecules are outside. Most of the small molecules are outside in the big, large beaker, and your protein stays in there, or whatever large molecule you're purifying, that stays in the bag because it can't fit through the holes in the bag. And the water can flow in along with whatever is dissolved in the water, like certain salts and buffer solutions, which we haven't talked about buffers, but buffers are solutions that maintain a constant pH, which keeps our proteins very stable. So you would do this, and maybe you do this a couple times. Some people do it overnight. You do it once or twice, and you can really get rid of a lot of small material and salts and things that you don't want mixed in with your protein or whatever you're purifying. Now, dialysis has a much more important role in treating patients, especially patients with end-stage kidney failure or kidney disease, where their kidneys are no longer doing that filtering job that they do of filtering all the excess salts and nitrogen compounds and some other things that are floating around in your blood that you build up over time that could cause damage to you. They become toxic after a while. We don't like calling them toxins because they all have purposes in the body, and most of these are useful. You just don't want high levels of them in your blood. So your kidney flushes them out into your urine, and then you excrete your urine out of your body. But if your kidneys are no longer working, you use what's called a dialysis machine, and you've all heard of this, and it uses a process called hemodialysis. So it's dialysis of the blood. You're flushing out some of the water, but mostly the salts and other compounds that will become toxic to you if they build up in high concentration in your blood. And what happens is you use large amounts of clean fluid. This is something like your blood, but it doesn't have all the cells and high salts in your blood. And you use that. It's called dialysate. And this will essentially help wash the materials out of your blood. And you flow it through this device, this big device that has these fibers in it. So instead of semi-permeable plastic-like membranes, these are actually hollow fibers that are semi-permeable, and blood can flow in through the top of this instrument and flow into these fibers, and it'll flow. The large blood cells are far too large to escape the fibers, and they'll just flow out and go right back into the patient again, out the bottom in this diagram. And these fibers are surrounded with this jacket of dialysate fluid, this clean fluid that will wash out through dialysis, through osmosis, through diffusion and ultrafiltration of these small toxic molecules they're toxic because they're building up, not because they're naturally toxic. The toxic levels will be washed out through the other side of this this instrument. So you end up with the waste dialysis coming out with the excess salts and nitrogen compounds that you're trying to get rid of out of the blood. And at the end, all but the only the largest components of the blood will be flushed back towards the patient, and that of course will be all the cells, the red blood cells, the various types of white cells, the platelets, and the large proteins that you need in your blood, like albumin and immunoglobulins and many, many other proteins that are in your blood, and those will go right through. So this is a very useful use of osmotic pressure combined with other diffusion and ultrafiltration.